research, experimental research in atomic molecular optical physics. He's an experimental physicist like me. And today he will present some insights in his most known research field, which is devoted to cold atoms, and using cold atoms for interferometry and to increase sensitivity of so-called quantum sensing. This quantum sensing is now a very vibrant field of research, as well as other quantum optics fields. And what is most important, he did his PhD in atomic physics in 2007, and under the supervision of Dr. Pramod at laboratories Castler, Dorsal of École Normale Supérieure. And he was working under work was devoted to the determination of the fine-tuned constant by combination of block oscillations and atom interferometry. He was also guest researcher at National Institute of Standard and Technology, so-called NIST in USA, and he was working during that time with laser cooling and strapping group, and he was led by Professor William Phillips and as a postdoc researcher in cold atom groups he did in French Aerospace Lab, FODERA, under the Dr. Alexander Bresson. He is co-author of 46 peer-reviewed papers in his research field, and it's worth of mentioning the most, I would say, important one. One is in physical review letters in 2008. Second, in Nature Communications in 2018. And one quite recent one is in a science group of papers. It's Science Advance, and it's published in 2024, and it's the most recent. Okay, hopefully we'll get some introductory talk, but before we start, we have some tradition in our company to make an appreciation of your visit, that you took effort, that we really appreciate that you will give us talk. We have some tradition of giving a bouquet of flowers. Please, Dina, proceed.
This is just a small appreciation.
And I welcome you to Dr. Malo, and it's a really great pleasure and privilege to have my friend after 15 years. So we are meeting after 15 years because I was working with him as my postdoc in Paris. So it's been 15 years, so it's nice to see you again. And of course we totally changed physically, but it's okay, it's a part of life. So I'm looking forward to listening this talk on the progress towards the development of quantum cold atom initial measurement system. So Dr. Malo, try to do this. Yeah, my experimentalist, but I wonder how to explain. If you have volume is very high, then if your volume is very high, it's only
Okay, so thank you very much. It's a real pleasure to be here and to be here with you, Pramod, after 15 years. So I'm very happy. So I will try to give you this little lecture. Hopefully, I hope it will not be too simple because I know there are specialists here. But I try to make it simple, but we can discuss afterwards if you want it simple, and hopefully it's not too hard too. So, okay, I will try to do my best to make it clear. Okay. So, so I'm going to talk today about quantum inertial sensing and the work we're doing in a collaboration between the French Aerospace Lab, Université Paris-Saclay, and Conservatoire National des Arts et Métiers, where the aim is to develop a quantum cold atom inertial measurement unit for navigation applications. And I'm going to tell you about the progress towards these developments. And inside this talk, I will try to give you insights, because maybe you're not familiar with this topic, on how atom interferometer works, and how from these atom interferometers we can extract the precision and accuracy inertial quantities such as acceleration and rotations. So, just a forward, you know that quantum physics provides the most accurate description of the world around us, and you know, guys, that quantum technologies are transforming communication, computing, information processing, but also sensing, and that's what it's going to be the goal of my talk today, to tell you how it influences sensing. And on the financial part, quantum sensing is projected to reach a $6 billion market by 2040 and disrupt industries that rely on sensor technology. But a question that may arise to you, as if you're not familiar with this, is what is quantum sensor? So basically, it's not a consensual definition, but a quantum sensor typically has some of the following characteristics that I will tell you right now. First, it uses quantum objects such as photons, atoms, or artificial qubits to measure a physical quantity, and this quantity can be time, can be gravity, can be any electric fields or magnetic fields. Another thing is that it's based on the basic principles of quantum mechanics that you know, superposition, entanglement, to perform the measurement. Additionally, it has some advantages, we hope it has some advantages over conventional sensors, thanks to some specific properties of the used quantum system. And as I will show you in this talk, it's not only limited to the sensitivity advantage that you can reach with the quantum sensors, it has also got other advantages. And finally, it could be limited by the quantum projection noise, and it could benefit from the use of what we call quantum resources, such as squeezing, to overcome this limitation. So here's the outline of this presentation. So it's divided essentially into three parts. In the first part, I will talk about inertial navigation with conventional classical sensors. Then I will move on to what we call inertial sensing using cold atom interferometry. So this is going to be part of the lecture. I will try to introduce how it works, the basic principles of cold atom interferometry. And then I will tell you about our research project, which aims at developing this cold atom IMU for field applications, which is really challenging. So first, a few words on inertial navigation with classical sensors. So maybe you know this, but today there are mainly two types of navigation systems which are available. The first one is the so-called GNSS, Global Navigation Satellite System. So unfortunately, this system is useless if the broadcasted signal from the satellites is unavailable or unreliable, which is the case for when you have a mobile system which are underwater, such as submarines, or when you're underground, because you cannot reach the signal. Or in case of defense applications, when you experience GNSS jamming or spoofing. So how do you do in these cases? So in these cases, you have an alternative, which is to use what we call inertial navigation systems. And the idea of inertial navigation system is to go for autonomous navigation. And the idea is very simple. The idea is the following: if you know where you were and you know how you are moving, you can extract where you are now thanks to some algorithms. And these inertial navigation systems are based on an IMU, an inertial measurement unit. And so what is an IMU? It's a set of 3 accelerometers and 3 gyroscopes. So, as you know, accelerometers are used to measure acceleration in the 3 directions of space, x, y, z. And the gyroscopes are used to measure the rotation rates in the 3 directions of space also. So for example, if you integrate your acceleration, you get the velocity, and if you integrate the velocity, you've got your position, and your gyroscopes give you your attitude. Okay? So with these systems, you can access through the algorithm by integrating the equations of laws of motion in your position. Unfortunately, the classical sensor suffers from a bias drift, which leads, after integration, to an error on the position of the vehicle, which increases with time. So this is not very good. This is essentially due, for example, to aging of the system, or thermal effects. So don't be worried about this table, but this is, so we can classify the accelerometers and gyroscope performances in terms of the position accuracy that you get when you estimate it after 1 hour of integration. So you can see that on the left-hand side, you have your IMU grade, which you can classify from the consumer grade, which is what you get in your smartphone, to the strategic grade that you get, for example, for submarines, for defense applications. And you have accelerometers and gyroscope bias in terms of bias stability. So the bias is the error you make on your measurement. For example, you go to weight yourself, okay? If there is a bias, you will have an error on your weight of, for example, 1 kilo. Here it's the same, but for acceleration measurements and for rotation rate measurements. And of course, what we want to target here is strategic applications. So meaning we want an accelerometer of bias stability at the level of 5 micro-G, where G is the acceleration on Earth. This leads to an uncertainty of 32, a few tens of meters after 1 hour integration time. And for the gyroscopes, we want to reach a gyroscope bias of a few nanoradian per second. Rotation of the Earth divided by 10,000 almost, okay, so it's very good. And what you have to know is that today's accuracy on the inertial navigation system is limited by the gyroscope at a few 100 meters. So we want to improve this. So this is a concrete example of what happens. For example, to come to Abu Dhabi, I took this wonderful airplane from Etihad Airways. And this wonderful airplane, I think it was equipped with typical inertial navigation system, where after 1 hour of integration, if you don't recalibrate it with an external device such as GNSS, you have a few hundred meter error on your location. This means that you can miss the airport at the end. So this is not very good because you want to land in the airport. So in fact, this is where comes quantum sensor into play. We think that ion quantum sensors are considered as serious candidates help inertial navigation systems by increasing their long-term stability and providing absolute measurements. And to do this, we're going to use a cold atom interferometry. So now I will dive into the cold atom interferometry. So here, we're going to take the advantage of the wave-like nature of atoms to create an atom interferometer that can measure the inertial quantities of interest, meaning acceleration and rotations, with extreme accuracy. So as you know from your old lecture of quantum mechanics, this duality between the wave and matter was extended from Einstein by the Broglie to matter waves, where you can see that the wavelength associated to matter is given by the Planck constant divided by the momentum of the particle. And the Planck constant sets the scale of the quantum interaction. So why do we use atoms as sensors? So as you might know, atoms of a certain species, for example, rubidium atom, are all identical in the universe, with a behavior which is dominated by fundamental constants. And by definition, a constant is constant over time. So this means that they are autocalibrated and they have an absence of drift over time. So this is why we're going to use atoms as sensors. But there are also other aspects of atoms that we're going to use. Atoms are massive, hence intrinsically more sensitive than photons to their environmental conditions, such as inertial fields, to want the sense. And atoms can be manipulated with laser beams, whose frequency is locked on a saturated absorption, meaning it's very well controlled. Additionally, as opposed to their classical counterpart, moving parts don't wear out, which is very interesting. And we're not only going to use atoms, we're going to use cold atoms. So what does it mean, cold atoms? Very fast. So when you have a gas, the narrower the velocity distribution, the longer interrogation time will be, and the sensor sensitivity will increase with the interrogation time, which is something that we can intuit which is very intuitive, in fact. And typically, we will need cold atoms, meaning root mean square velocities of about a centimeter per second, leading to microkelvin temperatures. So if you want a rough order of magnitude, if you take the molecules of nitrogen in this room, it's going at the speed of a jet plane, okay? So it's 300 meters per second. So we're going to go to a centimeter per second. Okay? So this leads to temperature of about a millionth of a degree above absolute zero. This is the coolest stuff in the universe. So it's impressive. Okay, so before moving to matter wave interferometer, I will talk about light interferometer that you all know very well here, I'm sure. So this is a Maxenter light interferometer. So how does it work? So it's a space-phase diagram. So you enter with a light beam here on the beam splitter. The beam splitter splits the electromagnetic wave into two paths. There's a couple of mirrors here. And then you interfere the electromagnetic wave and you count the number of photons on each detector. And as you know from your optics classes, you obtain, if you count the number of photons in the output ports, you obtain light fringes and a two-wave interference formula, where the phase shift, delta phi here in this equation, depends on the optical path length difference between the two arms of your Maxenter interferometer. Okay, this is the basic idea of a Maxenter light interferometer. So now what we're going to do is we're going to use light pulse atom interferometry. We're going to use light to manipulate the matter. So indeed what will happen is that the physics of an atom interferometer is very analogous to a Maxenter light interferometer with the role of light and matter, which will be interchanged. So what does it mean? As there are no natural beam splitters and mirrors for matter, we're going to use the interaction between light and matter to split and deflect the matter wave, which is created by the cold atom source. So this is a space-time diagram of a cold atom interferometer. So it resembles to a Maxenter light interferometer, so that's why we call it a Maxenter atom interferometer, except that the input state is not light, it's the matter wave. It's the cold atom gas, which we use as a matter wave source. Okay? So it enters the interferometers, and by adjusting 3 pairs of laser pulses, we arrive to split, deflect, and interfere the matter wave. And what we do in the end is we don't count the number of photons here, but we count the number of atoms in each output port of the interferometer using fluorescence detection. So we shine a laser beam here, and by monitoring the fluorescence of the atoms, we can go back to the number of atoms. And again, we have this two-wave interference formula, where here we can show that the phase shift depends on the acceleration or rotation of the atoms, or any other physical quantity, depending on the atom interferometer geometry. So here, with this geometry, you'll be sensitive to acceleration and rotation. So I told you we had to manipulate matter waves with light. So how do we do this? So here it's just for people who are not familiar with this, just a little, and for others it will be a reminder of atom-light interaction basic principles. So the idea, generally speaking, atom-light interaction involves single photon processes. So here, sorry for the one who knows, but for those who don't know, it would be interesting. So we consider a two-level atom with a ground state G and an excited state E, with their energy Eg and E. And if we send a photon on the atom with an energy HU, what happens if the energy of the photon corresponds to the difference in energy of the two states, then you have an absorption, and the atom initially in the electronic ground state will go in the electronic excited state. This is through conservation of energy. But you have also conservation of momentum, because as you know, light carries momentum. The momentum of a photon is h bar k, and when you send a photon of momentum h bar k on the atom, it gets kicked, okay? So it moves because it gets the momentum of the photon, and it recoils with a recoil velocity, which is typically for the medium atom 6 millimeters per second. So it's very small. The velocity of a snake, very, very small. Another thing I wanna want to point out here is that in real systems, you know that only the ground state of an atom has an infinite lifetime, whereas all the others have a probability of decaying in lower energy states. Meaning that when you shine your laser, when you shine your photon, okay, it goes in the excited state, but the excited state has got a finite lifetime, so typically for alkali atom, it's tens of nanoseconds. And this means that the atom will then de-excite via spontaneous decay by scattering a photon in random direction. So this is not good for our processes, because a short-lived excited state for the optical state will induce spontaneous decay and a loss of coherence in the line-pulse atom interferometer. Now, how do we circumvent this effect? So this means that to manipulate coherently the atomic wave packet in the interferometer, we need some lifetime of the excited state which must be greater than the atom interferometer duration. And typically, the atom interferometer duration is a fraction of a second. So how do we circumvent this? There are several strategies. I will only tell you about the strategy that we use. For alkali atoms, we use what we call two-photon atom optics. And the two-photon atom optics that we use is a stimulated two-photon Raman transition. In fact, here is a typical free level representing the rubidium atom with the two interfering ground states of the atom. These are metastable states, and we're going to couple these two states thanks to two lasers. The red laser with frequency omega-1 and wave vector k1, and blue laser with frequency omega-2 and wave vector k2. So in this process, we want to go from the ground state to the excited state. So what will happen is that first, starting with the ground state, the atom will absorb the red photon, it will recoil with the recoil velocity, like this, and then after, we're forced to make a stimulated emission in the blue laser, meaning it will reject this photon in the same direction, so it gets 2 times the photon momentum kick. So it gets 2 times the recoil velocity in this process. So this allows to have a kick which is an optical kick instead of the microwave kick here. And to do this, we put the two frequencies in one laser, which is in a one fiber optical fiber, which is Rathbone effect on the mirror. So this is how we circumvent the fact that if you're far detuned from the excitation state here, you don't have any spontaneous emission. But you reduce it a lot. So as I told you, sorry, my microphone is full. So the momentum transfer in this process is about 1 centimeter per second, because you get 2 times the photon momentum kick. And then, what is very important here in this process, and this is the key point, and it comes from quantum mechanics, when you make this optical pulse, you imprint the laser phase difference on the wave function of the atoms. And this laser phase difference comes from the laser phase difference between the red beam and the blue beam. Meaning if you go from the ground state to the excited state, you take a phase shift which is plus the phase, and if you go from the excited state to the ground state, you take minus the laser phase. And this means the following. It means, this is very important, it means that somehow you imprint on the phase of the wave function the position of the atom with respect to the mirror. So it's the way of putting the position of the atom in the phase of the wave function. So now how do we do the beam splitter and the mirror? So this three-level system, you can show that if you're far enough detuned from the one photon resonance, it's equivalent to a two-level system. Okay, and as any two-level system, it experiences Rabi flopping, as you learned in your lecture at the university. So to perform this, so if you go from the ground state to the excited state, depending on the duration of the pulse and the coupling strength, which is defined by what we call the Rabi frequency, but this is a detail, it goes through a sinusoidal excitation. This means that if you shine your laser during a time which corresponds to half a Rabi oscillation, you can put all your atoms from the ground state to the excited state, and you do the equivalent of a mirror. Now, if you shine your laser during a quarter of a Rabi oscillation, you put your wave packet in a superposition of ground state and excited state, and you mimic the effect of a beam splitter. So like this, you have the building blocks of your atom interferometer, meaning mirror and beam splitter for your matter wave. So now we want to calculate the phase shift with this interferometer. So how do we do this? Well, the only thing you have to remember is the phase rules that I just told you. Meaning when you go from the ground to excited, you take plus the phase, and when you go from the excited to the ground state, you take minus the phase. So what I propose you is to calculate the phase shift in this Mach-Zehnder interferometer. So we're going to go for the difference of phase between this path, and we're going to go and we're going to look for this output port. So if you take the upper path, you can see that time t equals 0, okay? You take plus the phase at time t equals 0, because you go from ground to excited. Then, if you look at the time t equals capital T, you take minus the phase. And then you take again plus the phase at time 2t. This is for the upper path of the interferometer. Now, if you look at the lower path, here you don't take any phase, then you take plus the phase at time capital T, and 0 at time capital 2t. So meaning that if you compute the phase difference, as the position of the atom is defined by acceleration, 1/2 AT squared, what you learn at high school, then your phase shift is KAT squared, where K is the effective wave vector of the light, A is the acceleration undergone by the atom, and T is the interrogation time. So you can see that you measure acceleration along the Raman laser, and that your sensitivity improves quadratically with the interrogation time. Meaning, the longer the interrogation time, the more sensitive you will be on your phase measurement. Unfortunately, when you want to improve time, you increase also the length of the apparatus. So you will have to find a trade-off, essentially for field applications. If you don't want a too big instrument, you have to also reduce speed. So there's a trade-off to find. Here it's a bit simplistic, but although it's a valid calculation for theoration, for Hamiltonian, which are at most quadratic in position and momentum, and it works for acceleration, rotation, gradient acceleration. Otherwise, you also have to account for phase shift in between the laser pulse, and eventually a phase shift which appears because you don't have a perfect recovery between the wave packet at the end of the interferometer. Okay, let's put some numbers. Let's put some numbers, okay? So this is our phase shift. So what is the minimum, what's the resolution we can get on the acceleration measurement? This is what is important. Well, it's the resolution you can get on your phase divided by this scale factor, which is the product of two things, the time of the interferometer that you know very well, and the frequency of your interferometer, the wavelength that you know very well also. So if you put some numbers, you can see that, well, before putting some numbers, you can see that if you have a large interrogation time, you'll be more sensitive, and if you have large wave packet separation, you're also very sensitive. So considering rubidium, whose wavelength is 780 nanometer, and a signal-to-noise ratio of 1000, meaning a sensitivity on the phase of 1 milliradian, for interrogation time of 20 milliseconds, you can reach sensitivity on acceleration of 10 to the minus 6 meter per second square, which is at the level of the best onboard accelerometer, you see, for small interrogation time. And if you want to go for long interrogation time, for example, by going into space or by building very big instruments of, for example, 10 meter tall, okay, you can reach acceleration at 10 to the minus 12 meter per second square, and this is very interesting to test the fundamental physics. So these are two applications of atom interferometry. I will mainly focus on this one. Okay, so let's have a look at the cold atom interferometry around the world. These are where people perform atom interferometry, so you can see that a lot of group in the US, a lot of group in Europe, also in China where they're very active, in Australia. No, not a lot in the Middle East, but we can do something if you want. I would be happy if you do this. So, atom interferometry and inertial sensing. It has got a variety of applications depending on the sensitivity. Main application today is gravimetry for geodesy application, but also for subsurface detection, oil, mineral, archaeology, bunkers, civil engineering, with a drastic reduction of the environmental impact, as no need for drilling operation. You just go with your sensor over, you don't have to drill, so this is very good. You have also all that deals with autonomous navigation, and also, for sure, with the basic physics, test of general relativity, test of foundations of quantum mechanics, gravitational wave detection, measurements of fundamental constants, and so on. So what's the operation principle of an atom interferometer? So the basic idea is to start with a cold atom gas, which will serve as a matter wave source in your interferometer. And to perform this, there's a standard technique which is called magnet-optical trap, and that is due essentially to the work of these three people, which obtained the Nobel Prize in 1997 for the development of methods to cool and trap atoms with laser light. So the idea is the following: you've got a gas of atom here, called the rubidium for us, and you send 3 pairs of light beams in the 3 directions of space, and you add some magnetic gradient field here, and this allows to trap and use the radiation pressure force to cool down the atoms. And typically, so we operate this in an ultra-high vacuum chamber, where the pressure is about 10 to the minus 9 millibar. We have typically 1 billion atoms in the trap. The temperature is about microkelvin, and the cloud size is about 1 millimeter. And once we have this, we have the matter wave source. Now we can start performing the atom interferometer. So what we do is we switch off the lights. If we switch off the light, the atoms fall under gravity. We perform a pi-over-2 pulse, which is a beam splitter pulse, a pi pulse, which deflects the wave packet, and last beam splitter pulse, which interferes the wave packet, and then we detect through fluorescence detection. And like this, we've got 1 point on the potential fringe of your interferometer. Of course, you have to start again the process in order to scan the fringes. How do we build a cold atom interferometer? Well, essentially, it's very simple. We need a laser system and a sensor head. So laser manipulation, as you saw, is key for the atom interferometer. So many frequencies are required for the laser cooling. This is the example of rubidium, where you need at least 5 laser frequency to cool down the atom and perform the atom interferometer. You need a precise control of frequency and intensity. And for the Raman transition, you need a perfect control of the phase difference between the 2 layers. Regarding the laser system, this was the old-fashioned way of doing the laser system in the 1990s. So typically you had a huge optical table in many optical elements, AOMs, mirrors, photodiode. This was very sensitive to disalignment, and of course it was not portable, and still used for lab-based experiments. But now, for example, at the French Aerospace Lab or in other companies dedicated to quantum inertial sensing, we have compacted the bench. And the idea is to use a compact laser architecture, essentially based on fiber telecom laser, which are at 1.5 micrometer, and using second harmonic generation. Why do we do this? Because at 1.5 micrometer, it's very robust, so you can put it for on-board applications, and second harmonic generation in all optical fiber system is very robust too. So it was experienced, for example, in this 0G Airbus, which is doing lots of parabola, and this was perfectly working. The sensor head, it could be titanium vacuum chamber or glass cell. Okay, you need a magnetic shield to protect from magnetic perturbation. You need multiple optical droopers to perform the atomic measurements, ion pumps to maintain the dry vacuum, and in order to have your atoms inside the cell, you can use, for example, an ampoule, okay, that you heat up, or dispenser, where you put a current inside, and through a Joule effect, it dissipates the rubidium inside the chamber. And this is typically what resembles our setup. It's a glass cell where here the atoms are trapped and then they fall down here, and this is under vacuum. Okay, but atom interferometer has got limitations. When a quantum sensor is taken out of the pristine lab and placed on a boat or an aircraft, such as this boat, in this condition, most of its advantages are lost. Now we're going to tackle real-world applications. So for in-field application, practical sensing capabilities of atom interferometers face 2 limitations that we'll try to explain to you right now. The first limitation is the following, it's the measurement range. As I showed you, the probability to be in one of the output port of the interferometer is a sinusoidal function of the phase shift, two-wave interference formula, where the interference period is related to the acceleration. So you can understand that when you put your system on a platform in a harsh environment, typically if you take, for example, an interrogation time of 20 milliseconds, the fringe period is 100 micro-G. You can imagine that the vibrations will be much larger than 100 micro-G. So the question is, where is your acceleration? For one probability output, you've got multiple values of the acceleration which are possible. So there is what we call a fringe ambiguity. We don't know what the acceleration is. And this is a big problem. And the second problem is the dead time in the measurement. As I showed you, our atomic interferometer is working sequentially, meaning there is a dead time during which we need to produce the cold atom source and we need to detect the atoms. And during this time, we don't measure the inertial quantity of interest, meaning we're only measuring the acceleration or the rotation during the interferometric stage. Meaning that during this dead time, you have a sequential operation. It means that you're sampling your measurement, and you know that when you sample, you can have all the noise at the multiple frequencies of your repetition rates can go back at low frequency and degrade the sensitivity of your sensor. So these are two effects which are really problematic if you want to put your sensor in a real field. So how to bypass these effects, or circumvent these effects? Well, the idea is, the following. For now, quantum sensors alone are not the solution, and we need to fuse this classical technology with the quantum technology. And to do this, we use a tool which is called hybridization, which means the data fusion of the two sensors, which are different but complementary. So here on the left-hand side, we've got the quantum sensor, and on the right-hand side, we've got the classical sensor, which is represented here by this Honeywell accelerometer. So we know that the quantum sensor is accurate, is highly sensitive, long-term stable, and has a control scale factor through interrogation time and frequency measurement. And on the other end, we know that the classical sensor suffers from gas and drifts. So what we're going to do here is that we're going to use the quantum sensor to correct the drift of the classical sensor. And we're going to use the classical sensors, which has a high data rate and a large bandwidth, to increase the dynamic range of the classical sensor, which suffers from dead time. And by doing this, we can get an absolute continuous measurement with a dynamic range compatible with onboard applications. So we take the best of the two technologies. And by doing this, we were able to perform the first quantum gravimeter to operate on a mobile platform. This result was obtained in HR Communication. And here you can see the sensor head of the gravimeter in this big orange box. And this big orange box is a gyro-stabilized platform because, of course, you want to measure gravity. Gravity is along the vertical, vertical is defined by gravity. But if your sensor, if you have swell, your sensor goes like this, you don't measure anymore. So you have to maintain the sensor head aligned along gravity. So this is what this orange box is used for. And you can see that the sensitivity is at the level of the micro-G. G, again, is the gravity acceleration. What I emphasize here is that the best accelerometers can reach 10 to the minus 10, 10 to the minus 11 G in terms of sensitivity. So when you go to onboard application, you lose sensitivity. And typically you lose 3 orders of magnitude. Factor of 1,000. But it works. So this is a good demonstration of how quantum sensor can be applied in the real world. So now we're going to move on to our project, which aims at building a complete cold atom IMU for onboard application, especially dedicated to navigation. So based on this hybridization principle, we will develop a hybrid atom IMU based on the periodic calibration of a classical IMU using 3 accelerometers and 3 gyroscopes using multi-axis atomic interferometer sensor. So how will it work? Well, the principle is very simple. At each measurement cycle, the atomic interferometer will measure one of the 6 inertial components. So the classical sensor will be necessary to process the atomic interferometer measurements in on-board environments. And the atom interferometer will correct the bias and scale factor of the classical sensor. And this is an equalized procedure. So this is a sketch of our lab setup. It's still not portable, of course. It's for now it's lab experiments. So here you have all the electronics and fiber optics at 150 at 1.5 micrometer. Here is the vacuum system to maintain the vacuum inside the apparatus. And here you have compensation coils to compensate for variations of magnetic fields. Here is our sketch of our system. So all the system is placed on a passive vibration and acceleration platform because even the lab would be considered as a harsh environment for our system. The Raman beam, which interrogates the atom, is retroreflect on this mirror. Okay. And here we have also loudspeakers to excite our system in order to mimic what could happen on a plane or a boat. So where are we at now on the project? So we need accelerometers and gyroscopes. So for the accelerometer, we are currently able to independently measure all components of acceleration in static conditions. So this is a result that we obtained in 2019 about measuring horizontal acceleration, which was a blocking point for the building up the inertial measurement unit, because it's not easy to measure horizontal acceleration. If you want to measure horizontal acceleration, you need to put your Raman laser in the horizontal direction. And of course, this limits the sensitivity of your apparatus because you can't get rid of gravity acceleration and your atoms are falling inside the laser beam. So what limits your sensitivity essentially is the fall of the atoms under gravity in the Raman beams. So we were able to, and we want something which is compact. So we don't want laser beams of 1 kilometer even if we had infinite power. Okay? So we reduce to 1 centimeter size laser beam. So this leads to integration time about 30 milliseconds. For people who knows about a little bit about metrology, when we measure, to characterize the sensitivity and stability of our sensor, we use what we call Allen standard deviation. So if you're not familiar with this tells you it's a statistical tool which tells you how noise averages as a function of time. So here you can see that we were able to measure the level of 10 to the minus 6 meters per second square at 1 second. We developed a novel technique, we'll not detail here, to address the atom in this configuration, and we obtained a sensitivity of 10 to the minus 5 meters per second square at 1 second integration time, which is compatible with navigation applications. So the goal is fulfilled. This is for accelerometers. Now for gyroscopes, this is where is the big challenge for quantum IMU. Why is the big challenge? Because to perform rotation measurements, you want to reach these sensitivity, these stabilities at the level of 10 to the minus 10 radian per second. And 10 to the minus 10 radian per second is 10,000 times better than the Earth rotation rate. We want to resolve this. To be at state-of-the-art navigation system using fiber optic gyroscope. You can reach this, but you can reach this with 2-meter height apparatus in the lab. And you can imagine that you can't put a 2-meter height apparatus on in a plane or a drone or something which is moving in a harsh environment. So all the challenge here is to reach this stability in a compact setup. So this is really, really challenging. So how do we proceed? First, we have to measure rotation rates. So, in presence of a rotation, the phase shift of magnetometer atom interferometer, there is an extra term which appears here, where the rotation here is the Coriolis term. So, here, KFT is the Raman laser, which sets the direction of the measurement. You have the acceleration that I showed you previously. But if you have an atom which is moving in rotating reference frame, then it couples to Coriolis acceleration like classical physics. So rotation couples to the velocity of the atom, and you can access the rotation rate through the measurement of the Coriolis accelerometer. So here is what I depict. Here is your interrogation laser. Here is the velocity of the atom. You always have velocity of the atom because you can't reach T equals 0 Kelvin. Absolute zero does not exist. You can't reach. So you always have thermal velocity. So your atom has got a velocity and then it drops like this, and you're sensitive to rotation rates which are orthogonal to the laser and to the transverse velocity. So the big problem, not big problem, it's not a big problem, but the problem here is that acceleration, linear acceleration and Coriolis acceleration are entangled in the phase. So how do you discriminate between the acceleration and the rotation rate? Well, theoretically it's always easy, but sometimes it's theoretically you can do anything. Prime is experimentally. So how do you do this? Well, if you find a way to launch the atom in one direction and the other, the Coriolis effect changes sign, and if you take the mean difference between the two, you can access or acceleration, or between the sum you can access the rotation rate. So that's what we're going to do. By making the mean difference, we can access the rotation phase shift. So here is the stage of what we have developed. Here is the magneton spectrum, so it's our cold atom cloud. Here is our cooling laser system. So what we do is we displace the mat by applying a magnetic field. Okay, here is the position of the cold atom cloud as a function of the current that we put in the coil. And then what we do, it's an original technique. We use a launch technique. We launch the atom in the interferometer using a Steiger-like force, which is based on the use of a magnetic field gradient. So we pulse a magnetic field gradient, and what happens is that we've got multiple atom clouds because at the end, we're not going through all the details, but at the end of the cooling process, all the atoms are in have got different polarizations, and we will only address one atom cloud that we launch with this process, and then we perform the atom interferometer, meaning beam splitter, deflection, and then interference. And typically, the size of the interferometer here is 10 centimeter height and 1 centimeter, which is given by the laser beam weight, essentially. The interrogation time is 40 milliseconds, and we launch the atom with a few centimeters per second using this technique. And then we detect the atom thanks to a detection beam. So when you do this, you perform one interferometer with one launch velocity. Okay? So you have to perform the symmetric. So experimentally, what you do, you take your cold atom cloud, put it now on the right hand side, and you launch in the other direction. Like this, after, through a differential measurement, you can access rotation rate. What was really tricky here is you see that you need to put your beam from one side up to the other. Now this is where the experimentalist comes into play. So how do we do this? We use a basic physics, we use a glass plate, and we put it on a rotation stage, a Torlat rotation stage, and we use the refraction of the beam when it changes angle of incidence. And when we do this, we can switch from this place for the detection beam to the other place, 1 centimeter away. And this is very funny, so I'll show you. This is the PhD student who thought about this. It was really genius. So the laser beam comes here. It goes through this plate, which is on the rotation stage. It goes inside the vacuum chamber, and in fact, it shifts like this. So you can see that with simple physics, sometimes it can help you to resolve some problems. Not always think complicated, think simple. Okay, so again, we perform the standard deviation of our measurements, and we obtain, I'm not going inside all the detail, let's let your computation science advances. This led to a sensitivity of 10 to the minus 5 radian per second. The possible limit of this sensitivity was vibration rejection, because I told you we perform the interferometer in one direction, we launch in one direction and then in the other. But it's not exactly the same acceleration measured at one shot and the other. So there is remaining acceleration which is not rejected between the two shots. So this is what limits the system, and if you put some numbers for the fundamental limit, which is limited by quantum projection noise, what we call the standard quantum limit, we should be there. This is the standard quantum limit, which is given by this expression, where Tc is the cycling time of the experiment, the launch velocity, the interrogation time, the wavelength of your laser, the contrast of the interferometer, and CPAC UPN is the detection noise, which is, if you divide it by the quantum projection noise, is 1 over square root of the number of atoms, or it could be 1 over square root of the number of photons if you do photons, right? The same process. So how can we improve this? Now, if we compare our results to what is performed for navigation, so here is the apparatus length as a function of the sensitivity, and here the stability. You can see that our result is here, so we've got typically 10 centimeter apparatus and a sensitivity which is here, where the best commercial gyroscope for navigation are here. So we need again to improve the sensitivity and always also the stability by 2 or 3 orders of magnitude. So how will we do this? Will we do this by making our interferometers simultaneously? We will launch 2 clouds of atoms at the same instant, at the same moment. And we'll interrogate the atoms simultaneously. Like this, we will reject this problem of acceleration which remains. This is the first thing. And the second thing is that we will use large momentum transfer atom interferometry, meaning instead of separating the atom wave packet by 2 times the photon momentum, we will give more photon kicks to the atoms in order to separate them largely and increase here by a factor of n the sensitivity. I want to emphasize here the quantum advantage. What we have done, I told you that we were hybridizing classical sensor and quantum sensor. Here again are Allen standard deviations. This in blue is the atomic measurement, which goes down as a function of time. Okay, so what we call white noise, it goes as 1 over square root of integration time. Yes. In orange, it's the classical sensor, and you can see that after, let's say, 1,000 seconds, it goes up, meaning the stability decreases. Okay, so this is the long-term stability is not good. And in green, it's the hybridized sensor. And this is an illustration of the quantum advantage, where the classical sensor was drifting. In fact, by hybridizing the classical sensor, which gives you a good sensitivity at short term and a bad stability at long term, here you copy the short-term sensitivity of the classical sensor and the long-term stability of the quantum sensor to the classical sensor. And here is an illustration of the quantum advantage of hybridizing a classical sensor with a quantum sensor, where you improve the long-term stability of the sensor. That's what we need to do for navigation. Of course, we have to improve the overall sensitivity, but already it's a demonstration of the working principle. I will give some conclusion and outlooks. So I hope I have shown you that inertial navigation using quantum sensor technology is a new field of research and development that could possibly alleviate some of the problems encountered in classical inertial navigation systems. Undersea, underground, and outer space navigation applications already cannot use GNSS as a reference due to non-availability. In such scenarios, quantum sensors may be the solution. I also showed you that operating a quantum sensor in the field remains challenging, as its performance degrades when submitted to a harsh environment. For now, only cold atom quantum gravimeter have demonstrated to be efficient for field applications. There is only one commercial industry-grade turnkey transportable quantum gravimeter, which is provided by the Exile Society. This is the gravimeter here, here, and all the electronics here on the boundary now, so they can monitor for preventing for volcano to explode, things like this. Their sensitivity is at the level of 10 to the minus 9 G, which is very good, 10 to the minus G. It's transportable, but it's not mobile. You can't put this on a mobile platform. Now, if you go for mobile application, you lose 3 orders of magnitude, but it's okay for accelerometers, you can find applications for this. And this is the only demonstration of a mobile application of a quantum gravimeter. Now, finally, our project aims at testing the possibility to develop an hybridized IMU fusioning classical and quantum sensors for onboard systems. The sensitivity for our accelerometers is now compatible with navigation applications. Radiation measurements still need to be improved by 3 orders of magnitude. And if we arrive to reach these stabilities in a compact atomic torsion size, in centimeter scale. We can imagine making this system transportable for applications in the field, as demonstrated with quantum gravimeter. This is the people that were involved in this work. I thank you for your attention.
Questions? Got a couple of questions. Thank you very much. It was very, very interesting. Mostly looking at it from the industrial perspective. I come from an industry background. So a couple of questions where I'd like to hear your thoughts and opinions. The first one is, apart from the few challenges which you highlighted, do you see further hurdles that you see to the commercialization or field deployment of this technology?
Sorry?
Any key hurdles that you see to the commercialization or field deployment of the IMU technology?
Any problems?
Yes.
No, because well, I mean, for now, the blocking points are mainly technical.
Right.
But I think we have all the resources technologically to go for in-field applications.
Right.
But we need to find the best way to go there.
Okay.
I think it will not be the problem, because we already can put accelerometers in the field.
I see.
Now we have to demonstrate the best way to circumvent, for example, problems of rotations. So we have to find ideas,
Right.
the best ideas. But after, I think we have everything to put this in
Right.
a laser system or performance.
Thank you. And then further on the aspects of system integration. So I previously worked with the prototyping project for a miniature chip scale atomic clock based on cesium atoms that we discussed previously. Do you see any possibilities for integration of a system integration where, say, the precise timekeeping capabilities of atomic clock is combined with the navigation capability of this system?
I think it's, well, yeah, the atomic clocks is for sure. I'm not a specialist in inertial navigation, but for sure, atomic clocks is interesting for inertial navigation.
Right, okay.
Separated from what we can provide with an IMU.
Right.
For sure, it's interesting. Yeah, just an atomic clock, miniaturized atomic clock for the inertial navigation system. It's
I see.
interesting.
Okay.
Yes, for sure, definitely.
So does that mean at current moment?
Now, combining the performance of the atomic clock with, in terms of what we need to reach in terms of sensitivity, I don't see what would be the gain.
Okay.
But definitely for INS systems, it's important. Yes. Yes. For
Thank
sure.
you. Dr. Nadia.
Okay, thank you for this nice talk. It was clear. Just I have a question regarding how do you excite this atom, the Rydberg atom, in the first slides. So first, you explained that thanks to lasers, you will make this model of the three-level atom to make excitation.
Yeah.
And then you also mentioned the magneto-optical trap. Do you still have to realize with these two lasers something like the EIT?
No.
No. So it's a magneto-optical trap.
Yeah, it's a magneto-optical trap.
Okay.
And then the atoms are released from the trap, and then we perform the two-photon transition.
So it's like a circularly polarized light with left and right, like sigma plus, sigma minus.
Yeah.
And then with the shift of energy, you realize the torque. Like, because we know that this momentum transfer is related to a torque, what we call a torque, which is.
Oh, there's no effect of this.
So what is the position? Like, do you rotate the atom, or it's like the tweezers, or?
No.
No. Okay.
No. In fact, the laser beams are coming with the same fiber with a linear polarization, and they are phase modulated.
Difference of phase is transmitted to the atom.
Yeah.
But then.
But the phase is Kx minus negative.
Okay. Okay.
Yeah.
All right. Then the last question is this transfer of momentum.
Yes.
Okay. It's 1 photon for each part.
Yeah. One for them.
Did you think about the Lagrangian to use? Like, yeah, like
More momentum.
more
deals
momentum.
With, he deals with linear momentum.
Yes.
Okay.
Yeah, linear
Yes.
momentum. Yeah. Yeah, we think about it by using, for example, put the atoms in the lattice and accelerate the lattice.
Yes,
So for
exactly.
multiple transition.
Yeah.
We do block oscillations.
Like Laplace.
Yeah.
Like because if you transfer more momentum,
We will do this, yes.
interesting, yeah.
I got practical question because I like the most the last slide, this one, with real application. Because the first one with the mountain is gravitometer. It means that it's only single axis or three of axis for the acceleration. Or it's only single. The commercial one.
The commercial one is single axis.
Single, but
There's no it does not exist in multiple axis.
and for the demonstrator, the red one, there are three axis or one axis?
No, one axis.
Okay.
One
And for example, to make three-axis system, it means that you need three separate cells, chambers with
No, one cell, so that's what I have.
like through other sides of the mirror, like windows. Yes, you can excite many beams.
So we put three laser beams. This direction, this direction.
Okay,
this
okay.
direction.
One chamber, at least one chamber.
And for each interrogation axis, you need a mirror to reflect your laser, and you stick a classical accelerometer to the mirror in order to correlate the classical acceleration measurement to the interferometer measurement.
Okay.
For each axis.
It means that this application can be quite easily extended to three axes. Quite easily, I think.
Quite easy.
Physically.
Quite easy.
Dr. Kadoret, just one, sorry.
Yeah,
Just
we can discuss
one
afterwards.
more technology-related question. In the next 5 to 10 years, do you see any particular scientific or technical breakthrough in the quantum sensing research that would enable or that would enhance the practicality of the cold IMU?
I think if we manage to reach 3 orders of magnitude that we're missing right now, then there will be a breakthrough. As it came from the gravimeter.
Right, okay.
Thank you for the talk. So I've been working on a theoretical quantum resource, entanglement coherence, so I'm trying to understand the connection between this application and the resource. So do you think like the quality of the amount of entanglement in the interferometer affects the accuracy of the technology, or like is there like study in that direction, like theoretical analytical like research on the amount of entanglement?
There are studies to see how, for example, entanglement or squeeze light would help improve the sensitivity of the sensor. So this is, first, theoretically it's interesting, because it's always interesting to look for physics beyond what we can do. It will mostly benefit, first, lab experiments. But as I said, when you go to real-world application, we're really far from this limit. We're first limited by classical effects. And even if we, for example, if we use entangled atoms or things like this, we can reach, for example, the Heisenberg limit.
Yeah.
Not advertised in 1 over n or 1 over n, but this is not the limitation here. It's far beyond what limits when you go for real-world application.
Maybe the qubit, because there you think about the 3-level atom. The qubit can use it as a quantum sensor. I think there are like some studies to use it as in metrology, the qubit.
But for what kind of sensing?
Quantum sensing.
Yeah, but what kind of quantum sensing?
I'm not sure.
Steve. Hi, thank you for the presentation. My question will be more on the hybridization using the classical and quantum sensing. What was the main challenge there? Did you have an issue regarding the synchronization of the two sensors? And did you, after calibration, what was the residual synchronization issue that you get?
Very good. Well, in fact, the classical sensor that you use must be well chosen first. After, the hybridization algorithm is a bit complicated because we need to calibrate also the classical sensor using the quantum accelerometer. So, in fact, I cannot explain all this because it's into the detail, but we change, for example, the interrogation time of the interferometer at the beginning, making, for example, with small interrogation time, the fringes are very large. So, like this, you can try to calibrate the sensor and then increase the interrogation time to be more and more precise. And what is very important, for example, is how you put your classical sensor on the mirror, which reflects the light. What is very important is because what senses the quantum sensor is not what senses the classical accelerometer. So, if, for example, it's not aligned, you have all the rotation effect which comes into the correlation and everything. So, there are lots of things like this that you have to be careful about. Yeah, exactly. So, and what was the limitation, to answer completely your question, it was the knowledge, the precise knowledge of the transfer function of the classical accelerometer.
Could you repeat?
The knowledge of the transfer function of the classical accelerometer.
So,
which, because you're submitted to acceleration which depends on frequency, and you have to know what's the response of your accelerometer in terms of frequency. So it's not, in the first case we took something which was equal to 1, whatever the frequency, but in fact it's not this. So we had to measure it. This was not given by the constructor, or it was not given with the right precision. So this is an issue. Yeah.
So if I go further, could we say that I understand that you may not have the same clock as well for the two sensors? Is that a common clock?
Not the same.
It's the same clock. I mean, what I mean by clock is we're talking about synchronization. Is that there is a clock behind, also
this was not an issue.
Oh, okay.
This was not an issue.
So okay, the noise from the clock was not affecting.
Okay, last question.
Yeah. So in the classical sensor, for as a gyroscope, do you mean fiber optic gyroscopes? In classical sensor,
Yeah.
in the gyroscopes, you just mentioned the last question that you need to choose the classical sensor.
Yeah.
So the gyroscope, are you comparing with the fiber optic gyroscopes? Fiber optic based gyroscopes?
Yes. So fiber optic gyroscopes are very good.
Mm-hmm. That's why I thought how they are.
There are still 3 orders of magnitude better. 1,000 times better than what we can do. But hopefully, and if we want to correct them, we would have to wait for a really, really long time, which has no interest. So we have to increase our short-term sensitivity, and then try to correct the fiber optic zero before it starts drifting. The fiber optic zeros are really, really good, but they drift. It's the limitation in inertial navigation. The ultimate, but whatever, even if we don't go for IMU, for example, having just a 3-axis accelerometer is very interesting for inertial navigation system. Because with a 3-axis accelerometer, you can access gravity, the vectorial gravimetry. This is very important in inertial navigation system because now they use some models. But if you have knowledge of what is the gravity vector, this is very interesting for inertial navigation system. So even though you don't reach the full IMU, if you just have a 3-axis accelerometer, it's already really interesting for IMS.
It means that if you know how depend the G along the globe. You can just use this as a reference.
Well, for example, with this experiment, we were able to do map of gravity. So what you can do, it's a scalar measurement, but what you can do is what we call gravity map matching. So you map the Earth, and then give your parameter, you come, you measure, and you know where you are.
Yes, very interesting.
Terrain navigation. But you can do this with magnetic fields or magnetic sensors.
Thank you. If there is no further questions, so thank you very much, Dr. Malo, for giving this fascinating talk. And I really like your last lecture to give the flavor about the marriage between classical and quantum data. And it's really a fascinating way to deal with the current requirement, current technology, the right time. So we should not wait for purely quantum system, or we cannot ignore purely classical. So it's always good to have the combined phenomena to improve this technology. So it's really great, and it's not very simple talk, but you make it very simple to grasp the non-scientific audience. So thank you very much. Thank you. If someone have any questions, so he is here. Tomorrow is here also, so we can have discussion.